said I would actually finish this problem for deflection and upload it for you, all finished, but I think we have time, so I would actually like to finish the deflection problem in this class. Then we will move on to indeterminate beams, which you need to know about for your project. So, and also making deflection continue another lecture, hopefully will refresh it in your mind. So, just to refresh your mind what this problem was, we had fixed at the bottom a crank beam with a point load of 10 at the tip, and the question was asking what this deflection was, what the vertical deflection was at the tip. Now if we look at this structure, the deflected shape shown here red in dashed, we get, you can effectively say we get deflection. This vertical deflection here is a result of the horizontal beam itself bending, and also as a result of this corner rotating. Okay? So when we do this problem, we actually will split it up into two parts, A, B and B, C, which is what I've done here. And when I've split it at the cut, I've had to, of course, draw all my internal forces in there. So I went through equilibrium and worked these out. And I said the steps we will go through to calculate this vertical deflection is, firstly, we look at AB. So for AB, we'll calculate the rotation at B, because it's only this rotation theta that we are interested in. And then once we have this rotation at B, when we come and look at BC, which is the horizontal beam, and calculate the deflection at C, we're going to use this slope here as our boundary condition, because this is our rotation. Because our boundary condition normally for a cantilever beam, which you'll be doing next week, at the support, deflection is 0, at the support where x is 0. When it comes to, and I didn't think I needed my beam, so I didn't bring it, slope is 0 at a fixed support as well. So we will be substituting in this value of theta that we calculate and using that as a boundary condition and then moving on to BC. So I got as far as I was analysing beam, the vertical component AB, and I said I'm just going to rotate it round because my mind, and I think most of your minds, work better when something is horizontal. So what you're seeing here is the beam AB rotated just 90 degrees to make our life easier. And what I'm after is I'm after the slope here. So I'm after the slope at B, and hopefully you remember our equation, d2y dx squared on EI is equal to our moment. And when we integrate, we integrate that once to get dy dx, and that is equal to our slope. And then when we integrate it a second time to get y is our deflection, which is what we're after. So with this problem here, I've created a free body diagram because what I'm trying to do is calculate my expression for my moment. We start off calculating a general expression for our moment. Then we equate it to EI d2y dx squared, and then we integrate it twice. That's the process you have to go through. So here I have here my free body diagram for section AB. I've cut at a distance x, and x in this case will be anything between 0 and 2 metres. And I come up with the general expression. Now to do that, you take moments at the cut. So I've drawn my m value in there, that's what I'm after. To be precise, I should have a shear in there as well for equilibrium. These two forces 20, 10 here, these are the reaction forces down here that I've calculated at the support. So taking moments at the cut now, I have m, I have plus 20. There is no vertical force in this case, so that's all I get for my moment. Now over here in purple, I wrote an x to the power of 0. When you have a moment, in general, to be able to switch it on and off using singularity functions, remember, we multiply it by distance to the power of 0. But in this case here, x to the power of 0 is always equal to 1. It's where you have x minus, say, 2 to the power of 0. This expression here either equals 0 or 1. And that is because we enforce the singularity rule first, and the singularity rule says if the number is negative, it disappears. Okay? So I know you all know any number to the power of 0 is equal to 1. enforce the singularity rule first. So a term like that is either 0 or 1, and that's the ability to switch it on and off. So when your moment, as is in this case here, is actually applied a distance x to the power of 0 away, that's always equal to 1. So when you integrate that, you just get x. So there's no need for me to include that, but if you like to be consistent, you can say every time I have a moment, I multiply it by distance to the power of 0. Okay, we've been through this, hopefully that rings a bell. Anyway, we now have an expression for our moment, so our moment is just equal to minus 20, and we equate the moment to EI d2y dx squared, and now I've done the first integration and I've got an expression for the slope. So this C here is my boundary condition, is my constant of integration, and I need to solve for that value of C there. So in order to solve for that value of C, I look back at my original situation here with the red line around it, and I look at what do I know about the slope here. So in this instance here, when x is equal to 0, my slope, dy dx, is equal to 0, and that is because at A, we have a fixed support. At A, there is a fixed support. And you know, at all fixed supports, the slope is equal to 0. So here, you would say, well, 0 is equal to 0 plus C, so therefore we know our constant of integration, C, is equal to 0. So moving on now, we have our expression for slope, dy dx, well, that we said was equal to minus 20x. And what is it we want to know? We want to know the slope at B. The slope at B. So B is when x is equal to 2 metres. So we need to substitute this 2 metres in here, and we'll actually get a value for the slope. Now, as yet, I haven't dealt with units, but we need to start looking about units here. Back in the original question, we were given EI in units of Newton millimetre squared. So we could either continue to work in kilonewton metres or decide to work in Newton millimetres. Normally, I would work in kilonewton metres and convert this to be kilonewton metre squared. However, today what I'm going to do is I'm going to work, because the solution I have in front of me does that, I'm going to work now in units of, of newtons and millimetres. So thus when I write my equation out now, this 20 value I got here, this was a moment. That was my moment, and that 20 was in kilonewton metre units. So thus in here now, I'm going to write it as 20 by 10 to the 6, because I'm now converting it to Newton millimetres, and I'm going to multiply that by 2,000, because that's my distance in millimetres. So now I get a value of 4 times 10 to the 10. So therefore, my slope is equal to 4 times 10 to the 10. So this becomes the boundary condition for BC beam. So now we can look at BC beam. And when I consider BC, I have, so this is now BC. Now, looking back, I was saying when we look at BC, we know the moment here it's 20 in the corner and the force up, the shear force up is 10. So this corner here is B, and I'm cutting it just before C. So here I effectively have a known shear force of 10 kilonewtons and a known moment of 20. So I'm making my cut at x metres. and I draw my unknown internal moment because that's what I'm after. So now, taking moments at the cut, I have m, which is my unknown internal moment. Then I have plus 20. I'm going to multiply that by 10 to the 6 now to change my units to Newton millimetres. And then I'll have minus, and I'm going to convert that to newtons, 10 times x. And all of that equals 0. So here is my expression for my moment. And I am doing it in these units, but I don't advise you to, and I don't advise you to generally, because you can see I've got 10 to the 3s and 10 to the 6s everywhere. So that we know is equal to EI d2y dx squared. So we are then going to integrate once to get the slope. And we get this. Now it is at this point here that we can actually use our boundary condition, because the slope, as I drew in the other picture, here is actually equal to the slope going around the corner. Because it's a corner, it stays at 90 degrees, and however it rotates in the vertical is how it rotates in the horizontal. So, if we now substitute in here, so we're going to substitute in when x is 0, dy dx is equal to, and we come back here, and what did we say dy dx was equal to? We said it was equal to, where was it? Where was it? So we've gone too far. Sorry. Here it is. So dy dx is actually equal to minus 4 divided by EI. So, this is our boundary condition. So subbing this in now as our boundary condition. When x is 0, you can see this first term here is 0. The second term here is 0. So we're left with EI dy dx is equal to minus 4 by 10 to the 10. Oops, where did I have the EI? Oops, hang on. I always muddle up my EIs. They cancel out. They should be cancelling out. Humour me. Humour me, humour me, humour me. If anyone can see my mistake, don't call it out, because I'm going to go, what? Don't understand you. Confused. Hang on. Give me a minute. Talk amongst yourselves. Oh, I make this mistake every year. Dy dx is minus 10. Huh. Oh, okay. Here I say dy dx is equal to minus 4 by 10 to the 10 on EI. So here, that means EI dy dx is just equal to 4 by 10 to the 10. Shh. Okay. So we go back plus C. Sorry. Oh, sorry. So, EI dy dx, which on the other page we said was equal to minus 4 by 10 to the 10, plus C equals 0.
So therefore, we have a value for our constant of integration. It's equal to 4 by 10 to the 10. So back in my equation on the other page, I'll rewrite it. I had that plus C, so I can now substitute in for C. And I now need to integrate it, differentiate it one more time. Now my second boundary condition, what's that equal to? It's equal to the displacement in the vertical plane here. And the displacement in the vertical plane here is effectively equal to 0. So my second boundary condition is when x is 0, y is 0. And if you substitute that in here, you will get d is equal to 0. So my final expression for the vertical deflection in BC is equal to, drum roll, that. And we want to know the deflection at the tip. That's when x is equal to 2 metres. And I'll leave you, please substitute in yourself, get your units all right and work this out. You end up getting deflection of 53.3 mil minus, the minus means it deflects downwards. Okay. That is a difficult question, so please go away and try and process it. Okay, that now brings us to the end of deflections. And we can't possibly have a break now. It's way too early. We're starting on our final topic. Yay! Indeterminacy. Yep. Isn't it what, sorry? It's minuscule. No, the vertical displacement is minor. So someone's asking about the vertical displacement. Someone's asking me, what is the vertical, isn't there some displacement here? You're saying that there? You're saying why is that displacement value there 0? This displacement here, the only reason you'd have a shortening here is because you have 10 kilonewtons acting in your column, and the shortening here, I don't know if you remember the formula yet, how much revision you've done, will be PL on AE. Remember we did the formula for how much something will shorten or lengthen? If you actually, you don't know the area of the beam, but if you would put the area of the beam in, the Young's modulus in, and the length, you would find the displacement values you get in there are point something millimetres. So it's effectively negligible. So the deflection at this tip here, as I said, is a result of being BC bending, curving, and a result of the fact that that corner rotates. So, hang on. Let me just add one more slide in, since you're interested. So you could actually, excuse me. You could actually look at this deflection here and say, well, that's actually equivalent to me saying that corner is fixed. And that displacement in here, I'll call that delta 1, plus just the displacement caused by that corner rotating theta. So if that length there is L, that amount of movement there is theta times L. So this total displacement here is my delta 1, the displacement from the beam bending, assume it's the corner doesn't rotate, and then the fact that if I just rotate the corner, that point will move down as a consequence. Yeah? So the amount, if you wanted to be precise, you could then say it was plus PL on AE, yeah? Where that is P, but this term here is effectively negligible. The other's 53 mil. That will be very minor. Okay, moving on to our final topic, indeterminacy, which you need for your project. So hopefully we'll finish indeterminate beams today. So you've then got all the theory for your project. And we'll tackle indeterminate axially loaded members next week. So, I love to tell you how much you've learned. You should appreciate things in life. Appreciate the fact that you've learned a lot in this course. We know about loads, we know how to calculate reactions, you know how to analyse trusses, you know how to analyse beams. But in both those cases, they had to be determinate. And what does determinate mean? Determinate is when the reactions can be calculated using only the 3 equations of equilibrium. So, when reactions can't be calculated using the 3 equations of equilibrium, the structure is indeterminate. So we now are going to look at indeterminate structures. Very complicated, so we're just going to look at the 2 simplest cases where you have axially loaded structures, just axially loaded beams, and then we're going to look at axially loaded members. So if that's fixed, and for instance, I've got to make it indeterminate, that's fixed. So you're going to say, how does it squash? So how about I show that as fixed and that as fixed, and I say I have a load here, an axial load in the member here. What are all my reactions equal to? So I'll show you how to do that next week. In terms of an indeterminate beam, I'll show you them in a minute. So, determinate, indeterminate, reactions aren't enough. So here are some determinate structures here. Here's a truss member, and here is a beam. So in each of these cases, you could easily analyse, find your reactions, draw your bending moment, your shear force diagram. Here, method of joints, you could solve for those 2 unknowns, then come down here and continue on. Here are some indeterminate structures. So when a structure is indeterminate, there's a choice of load paths from the load to the support. What I mean by that is I could take out this middle member here and it's still triangulated, so the loads would then travel down the other 2 members. I could take out this bottom member here and the load would still travel down into the other 2 members because it's still triangulated. In this system here, I could take out that middle support here and then it would just be a simply supported beam. So it's not to say it won't collapse if you take that support up because the load's too great, but it's still stable. And we call these extra supports on members redundancies. So we have more in there than in what is required to be stable. So what are the advantages? Why do we have indeterminate structures? Why do we have more supports than we need? Why do we have more members in our truss? Well, we end up getting smaller forces and stresses in our members, so we can have smaller members. Our structure is also then becomes stiffer. It doesn't deflect as much. So therefore, if it doesn't deflect as much, we can put smaller members in again, and it's redundant. What I mean by that is if you then blew up one of the supports, so if you come back here and we blew up this support here, our structure would fall down, it would collapse. So if you blew up the support here, the structure would still remain standing, it would still remain stable. Okay, so if you're building in the middle of a war zone, put some redundancies into your structures. Disadvantages are that you then start getting stresses occurring when you get settlement and when you get temperature variation. So I'll talk more about that. So let's look at smaller stresses and deflections. On the left-hand side here, I have a simply supported beam with a UDL load on it. You draw the shear force diagram, my bending moment diagram. This maximum moment in here is equal to WL squared on 8. If you would work with the fact that that is WL and the length of this beam is L. If we have the same beam, but now we've fixed our supports here. If you look at the deflected shape here,
because we know the rotation equals 0 at a fixed support, our structure deflects far less. So therefore we wouldn't require as big a beam for serviceability limit state design. When we look at our bending moment diagram, our bending moment diagram actually it's pulled up. So we have a moment at this end, WL squared on 12, and a moment down here, WL squared on 24. So the overall moment is still WL squared on 8, but these two moments are smaller. So thus, we could put a smaller beam in there. So, yay, why don't we always make structures redundant? And I'll tell you in a minute. So indeterminate structures are redundant. So that potentially gives them the capacity to redistribute loads in case of extreme earthquakes. So as I said, if you have accidental loading, earthquake loading, war loading, okay, and certain members of your structure are removed, okay, then the structure will not necessarily collapse. The loads will redistribute and it will still stand. So here's an example of that. Here is a beam, and if we did a n plus r is equal to 2j, so let's assume there's no joint here. Hopefully you remember this from the first quiz. So let's say there's no joint there. So if I did m in here now, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 members. Hopefully I'm going to get this right. Reactions here, 3. Number of joints, 1, 2, 3, 4, 5, 6. J is equal to 6. So m plus r here is equal to 13. Yay. And 2j is equal to 12. So this is telling us it's indeterminate. So that means if you attempt to do a method of joints here, you would get stuck. You go, no, there's more than 2 unknowns here. Oh, no, I can't calculate all the internal forces. So if there was an earthquake or something and one of these members collapsed, you could see here we still are left with a stable structure. So our structure would still stand. If our other member in here was removed, once again, we have a different load path. The loads will travel a different way, but we still have a stable structure. So that's what I mean by indeterminacies. So that's an advantage. So here we have here a prop cantilever beam. If you actually draw your stick drawing, this column here provides a support upwards, and at this end here it's fixed into the wall. So we have 4 unknowns here. So this is an indeterminate beam where you have 4 reactions, only 3 equations, and if you have a difference of 1 here, we say the beam has 1 redundant or 1 extra force. So in effect, if a car came in, let's assume this is a petrol station and a car came in and it slammed into that column here and thus removed the column, assuming it's not a really windy day and there's no snow on the top of it and there's no maintenance men on the top of it, you know, this thing here would not necessarily collapse. Oh, it shouldn't, yeah? Okay. They are the advantages. Here's the disadvantage. Stresses will occur due to temperature variations. So in a determinate simply supported beam, you have a pin at one end and a roller at the other end. And we all know on a hot day, the steel beam would expand, and because this is a roller support, okay, that expansion will just occur. However, if you have an indeterminate structure, so both supports here are pin supports, when it heats up and it tries to expand, it can't, because the 2 supports are fixed. So don't worry about these formulas here, you'll see them in second year if you choose to do civil engineering. You actually get forces, I was going to say if you pass, but I better not say that. If you choose to do civil engineering, of course you're all going to pass. Everyone in this room will pass, because every other chair in this room should be filled. So it's the people that aren't here. That's not true necessarily, so I shouldn't say that. They may be watching this as we speak. Hello to you all. Okay, so for this indeterminate structure here, can you see the 2 ends can't move? It heats up, it's a hot day. It tries to expand, it can't. If it is hot enough, what's going to happen to this thing in the end? It might potentially buckle. Yeah? There's an axially loaded member there. So you get these other forces in there that you mightn't have thought about. So that's one disadvantage due to temperature. And we all know on bridges, you know, when you drive over bridges and you hear ba-bum and you drive over that jointing in the bridge, ba-bum, 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 they are all the joints in there to allow that bridge to expand thermally. and contract in hot and cold weather. So you don't get these extra forces being developed, causing the concrete to, well, extra stresses, and also causing things to crack. Okay, another disadvantage is when you have settlement. So here is an example of your project, which I will talk about as well. Here is the option 2, where you have 2 beams simply supported. So if I was drawing that here, I would draw it as 2 separate beams. I'll put the pin support in the middle and say we have a roller here and a roller here. Now a structure like that, because the jointing will allow movement to occur, there'll be no stresses occurring due to temperature effect. And if that middle support settled, you would just get that middle support settling. You wouldn't get any extra forces developed. You might be going, why not? Think back to when we did the problem way back in week 3, I think, where we had a point load on a beam, and then we put that beam at an angle and kept the same support type, and you had to calculate those reactions again, and you discovered they were the same reactions. So you get no extra forces, reactions occurring due to settlement. If you have an indeterminate structure, however, this beam is continuous. So this is this final case you have to analyse in the project, where your beam runs continuously over that central support. We have one beam with a support in the middle. So can you see, if you move this support down here, because this is a continuous beam, it will bend. It's curving. If it's curving, there's a bending moment in there. So before even you start putting load on there, if there's a bending moment in there, there are stresses in there already. So they are the 2 disadvantages over the advantages. So you would have to assess what's more worthwhile, or you would just say, okay, well, I just have to take into account. And quite often, when you look at structures, as well as dead load, live load, you have temperature loads. You have settlement loads as a load case. So you would consider those as load cases. Okay, our structures are indeterminate, so what do? Equilibrium is not enough. So when I talk equilibrium, what am I talking here? I'm talking about my forces in the x direction, my forces in the y direction, and all my moments on my system are in equilibrium. So I now have to consider compatibility, which is a really big word. Okay, what is compatibility? Compatibility considerations require us to look at the internal deformations or the external displacements in a system. So we have to consider how the system is moving. The structure must fit together with no gaps or overlaps, and the deflected shape must be consistent with the support constraints. Sounds very complicated. It is not. I'll walk you through a couple of problems, and I'm sure you'll get it. Now, please concentrate really, really, really hard, because this is always the worst done question on the exam, because I think people do it as the final topic and then they go, I don't need to revise it, but you do need to revise it. Okay? Okay, so we're going to look now at indeterminate beams, and we're going to look at indeterminate axially loaded members next week. So, to solve for indeterminate beams, we use the principle of superposition. Which, have you met the principle of superposition before? It states the effects of each load can be calculated separately and added together to obtain the effect of all the loads applied together. And I should have brought my ruler with me. If I tell you when I put one apple on my, call this a ruler, it deflects down 5 mil. If I put 2 apples on there, how much is it going to deflect down? 10 mil. So you are using superposition. You're saying if I got 5, if I put 1 on, I get 5. If I put 2 on, I get 10. So what we're going to do is we're going to turn our system into 2 determinate systems and deal with it that way. Okay, so here's an example here for a determinate beam. Say you were given this problem to do in the exam and you went, God, I have no idea how to draw that bending moment diagram. What you could do is you could separate it out. You could say, I know how to deal with 1-point load, but I have no idea how to deal with 2-point loads. So you could actually apply to your determinate beam 1-point load and apply the 2nd-point load. You can work out your deflected shapes and bending moment diagrams separately and then superimpose them. And voila, you would have the correct bending moment diagram.
So that is the principle of superposition. The thing to note with the principle of superposition, it only applies if things are linear elastic. Okay, moving on. So have a look at our beam here. Is it determinate? Is it indeterminate? We have 4 unknown reactions. It's indeterminate. So at this point in time, you would go, well, I can't work out this problem. There's no internal pin in there, so I haven't got any extra information, but you now can cope with that. What you're going to do is you are going to split it into 2 systems. You're going to create what we call a primary system, and that system is going to be determinate. So you're going to create 2 primary systems, 2 systems that are determinate, and then you're going to link them by compatibility. So we create a primary determinate system by removing one reaction, and then we calculate the deflection at that point. So here we are here. I've said let's take away support C. Taking away support C, it's just a simply supported beam. Easy peasy. And you can all calculate the deflection here, because you've all just learned how to calculate deflections. So where is that getting us? Okay. Oh, before I go on, now calculating that deflection there, you may say, yes, I can do it, but it's going to take me half an hour. So what we do is we give you useful information. So calculating the deflections from first principles, okay, is a long process. So you're saying, oh, so I don't have to know how to do it now. Yes, you do, because there's one deflection question on the exam. But when you come to do your indeterminate question, you will be given useful information. You will be given the equation already. So when we solve indeterminate problems, we generally use published deflection formulas, and they look like so. So let's have a look at these 2 formulas here so you know how to read them. I have a simply supported here beam with the force P on it. This is V, they're calling deflection here. Well, that's not, whatever that is in symbol Greek form, I don't know what letter that is, I'm going to call it V. What is it? Gamma, alpha, beta, what one is that? We'll call it V. Okay, so V is the deflection. So when you read these formulas, you're generally given 2 formulas here. So in this case here, this is telling us this is the deflection when x is equal to A. So when x is equal to A here, that you can see that's the deflection actually under the point load here. And then you're given a second formula, and this is your general equation. This is the equations you develop when you use the integration method. You get a general equation here, and you can see the range here. Well, in this case, this equation is only valid between 0 and A. So it's only valid in there. Unfortunately, when you look up these equations, they never use singularity functions. So they always give you the full deflection in two equations. We're clever. We know how to use singularity functions. We could come up one expression for that beam that would be valid for the entire beam. But the published data doesn't. Okay? So you've got 2 terms here. So over here we have a cantilever beam. So x we effectively take as x. You can see the axis on here, running from the left to the right. So when we look at our expression here, they call it V max, which happens to be equal to the deflection under the point load. And then we get our general equation over here. Now, this general equation over here, I'll prove to you that that will yield that maximum value. If I substitute in when x is equal to L here, I would get my deflection is equal to P L squared on 6EI, 3L minus L, and lo and behold, that gives you that value there. So one is always a general equation, and one, because you usually want them at a particular point, they'll give you a shortcut equation. Okay, so we've created our primary determinate system by removing a load, and we've been able to calculate the deflection there by using formula. What we then do is we apply the removed reaction, we reapply it as if it's a load. So we apply the removed redundant reaction as a load, and we calculate the deflection there in terms of our unknown reaction. So we have put back here, we've said let's call this unknown reaction CY, and we've come along here and we've said, okay, I'm now going to apply
that removed reaction, that redundant reaction, hence called the redundant system, as if it's a load. And I'm going to calculate this deflection here as C. Where is this all going, you're saying? This is where we link it by applying compatibility. At the removed support, the deflection has a known compatibility relationship. What am I talking about? Okay, tell me, what is the deflection at C equal to? What's this deflection here equal to? It's 0. So there is my compatibility relationship. We have a 0 deflection here. So we've said when you take it away, you get a deflection delta P. When you apply it as an unknown, you get a deflection delta R. And the compatibility relationship says if you add these two deflections together, they have to add up to 0. So this, in effect, is my fourth equation. 4 unknowns, 3 equilibrium equations, 1 compatibility equation. So, again, looks to be a bit of a mouthful. We do a problem, you'll see it's not. And then finally, you solve for your reactions, of course. Once you have one reaction, once you know this value of Cy, then, of course, your system is now determinate again. So you can then solve for all your other reactions. Okay, let's look at this problem here. We have a point load on a beam that has 3 supports. So it's 4 unknowns. So we are going to assume our reaction at B is the redundant. It could be A or it could be C, but we're just going to take the one at B. Which one do you take away? Are you in the exams stressing about which one to take away? No, because the useful information we give you is very useful. It will hint to you which one to take away. It doesn't matter which one you take away. You'll always end up at the same answer, but that will indicate which one to take away. Okay, so we're taking away support B. So what we now need to do is calculate this point here is point B. So we're removing it, but we're going to calculate this deflection at B. And then we've put it back here as this By here is our unknown. So when we calculate this deflection here, B dash B, that is going to be as a function of our unknown reaction By. And then when we equate them in our compatibility equation, that's where you'll solve for By. Make sense? Okay, let's get some numbers happening then. Here is our useful information. But as I said, unfortunately, it only relates to, and this is the complication, it only relates to between that point and that point. So this equation, oh no, it doesn't even relate that far. You can see here it's only valid between 0 and A, so it's only valid up to the point load. So this equation is only valid between the support and the point load. But in saying that, how about I just rotate? We want this deflection over here. It's not within the range we want it to be, is it? So why don't I just rotate my beam on a vertical axis? So I'm just going to turn it round here. That's my 20 kilonewton here. That's at 2 metres. There's a support here. There's a support here. There's my deflected shape. We want to know the deflection here, VB. That's 2 metres and that's 4 metres. So can you see here I've got the same beam now? But when I look at my useful information, now the range in which it is valid is between the left support and the point load. So now it's valid between 0 and 6 metres, whereas here it was only valid between 0 and 2 metres. So sometimes you have to be a bit clever with the information you're given. So all I've done is I've rotated my beam round because I know where I want the deflection in its original form, I can't calculate that value there because that doesn't fit within the range. Does that make sense? Okay, so here's our equation, and we plug into this equation. So L here is the entire length of the beam, is 8 metres. The way I've rotated it round, B here, oops, tell me what B is equal to. I rotated it around here. Now I'm comparing these two systems. B is the distance between the point load and the support. So B here is equal to 2 metres. And X is the location where we want to know the deflection. I want to know the deflection here. So X here is equal to 4 metres. Does that make sense? Okay, so we plug into our equation or our values and we get a value. We'll leave it in terms of EI. That's my primary beam. Now I go to my redundant beam. My redundant beam is where I apply what I took away. So do not, on top of this, put your load on as well, because then you would be doubling up on yourself. So you look at your system, you put back what you took away. The other piece of useful information for this problem is as drawn here. Now, as drawn here, V max, because it's symmetrical, well, that gives you the deflection in the middle of the beam. And this is the general expression for V. Where do we want the deflection? We're looking for this deflection here, which is effectively in the middle of the beam. So we can now use the simple equation this time. So plugging in here, L is 8 metres, and we keep it in terms of By. So I have my two deflections, VB and V-B. And now I apply compatibility. So compatibility states that if I go back here, what is she talking about? These two deflections, as calculated, have to add up to 0. So here are the two terms for my two equations. Note one other thing. When this formula, as written here, this formula here has a negative sign in front of it because it's moving downwards. When we applied our unknown here, it was acting upwards. And thus, our deflection is positive. So again, you are looking at the formula and you are changing it to suit your case. So now when we add the two together, one's a negative, one's a positive values, we equate them, we get a value for By. Once we have a value of By, 13.75, we can then just use our 3 equilibrium equations to solve for our other 3 unknowns. And Bob's your uncle. My dad's a New Australian. He used to say when he was here and they used to say, Bob's your uncle, he'd go, no, Bob's not my uncle. But the classic one he said that used to get him, well, got him originally, was when they used to have a party or a do at work, they would say, bring a plate. So he brought a plate. Because he didn't get, bring a plate means plate and something on top of it. Anyway, before we do this, I'm going to show you something to wake you up a little bit. Here is an old exam paper problem. We'll do that one next. Actually, I don't want to do that one because that's pretty well what you have to do in the project. I never realised that. Oh, I'm going to do it not in general terms, so I'll leave you to do it in general terms. Okay, hang on. Keep. You may have seen this before. Following on from sustainability on Monday where people walked out on me very rudely. And I cited a few examples on Monday, being the Milwaukee Art Gallery with the Calatrava wings that opened up. Now, you probably, would have to admit that's probably not a sustainable structure, but that was trying to make use of an efficient, well, was trying to, it wasn't even a passive design because it moved, but I thought it was a good structure to put in there, but it was a means of applying sun shading to improve the energy efficiency of your structure. You leaving now just because I said people were leaving? Yeah, bye. Don't be so rude. Anyway, moving on. Have you all seen this before? This was a proposal put out a few years ago, or maybe 6 or 7 years ago in Dubai, when Dubai had lots of money, to design an energy efficient structure. And they proposed to build a structure where every floor rotated independently. So architecturally speaking, wow, it changes shape all the time. So this structure was to be powered entirely, the proposal was, by the sun and the wind energy. Architects claimed it would generate 10 times more energy than that required. So to get that energy, there were solar panels on the roof and 48 wind turbines sandwiched between the rotating floors. So let's have a look at it. So here is the core. Remember when I did deflections, we always have a big concrete core to provide you with your lateral stability. Circular core here with elevators to put your Ferrari in, because if you have an apartment here, you have to have a red Ferrari. So here are the people elevators. You can see here the people elevators, but you had to have your big elevators too to park your Ferrari up there. So you can see here, okay, I never even noticed that before. You have the hotel levels where you have lots of escalators, and in the villa levels you've only got a few that go up further. So here is each floor with the Ferrari once again featuring, travelling up. And you can see the wind turbines sandwiched between each floor, and you can also see the other cars in there too, the yellow one and the blue one. So you had wind turbines in here. Now my first issue is you hear about all this complaining of people that live out near wind farms, how noisy it is. And they're they're like a kilometre away from the wind turbines. I don't know how you could have this wind turbine spinning under you and actually not hear that. But I think it's a great idea. So you have your wind turbines in there, it's windy, it spins these wind turbines. Of course, there's the Ferrari again. So how they proposed to build this was to build the central core and then have these pre-made up sections that they lift up into place. So quite clever the way they erected this. So a lot of pre-cast, pre-made sections. You have to have a sunflower in there to make it look really green and environmental, and a couple of wind turbines, a bit of water too, makes you feel good. So even some rose petals, does it make you feel green and sustainable? So natural energy, they did explain how, with the wind flowing through, you would get the turbine spinning. And now we look at the floors, and with your Ferrari, you've always got to have your lovely slim woman as well. And here she is out on the deck chair. So they also had balconies that can then extend out further, so you could catch some more rays. Yep, so we've got that, our extendable balconies. And then you have plan views of the apartments. Now, the issue I have here is this apartment, you've got 1, 2, 3, 4, 5, 6, 7, 8 or so apartments on one floor. Now, if you want the sunny side of your building and you press the button to rotate your floor around, I don't know, we have enough problem with the remote control in our house. I have no idea how you would share who gets the sunny side. So that's the other issue I have with this not quite being realistic. As you move up the tower, so you can see up here in this diagram here, it shows you've got A, C, D, the different apartments. As you move up, the individual apartments get bigger. And when you get further up the top, you've just got the one villa. So here's your villa floor, then you would have control over which side got the sun, because you've got the whole floor and you've got 2 Ferraris, and you've got your home cinema. So here it is at night, looks great. During the day, and I love this final one. See this bathroom? It's got a pool in it. Check this out. Hang on. There's all the images. Looks great. Look at this pool here. So what am I trying to tell you by showing you this? Not much, really. I'm just trying to amuse you. No, but I suppose the other thing I want to say is, like, it's great that these architects have come up with this, because the more we push the boundaries, the more creativity and the more development will occur. But this was proposed about 10 years ago, and it hasn't been built. Because maybe there are a few flaws in it, but the concept, the idea itself is fabulous, the fact that they're trying to integrate all these sustainability things in there. So if you want to be involved in something like that, you've got to know about indeterminate beams, don't you? Okay, I'm going to do this problem very quickly. No, I don't want to do it, actually. I'm going to do the second example. Okay, now in saying that, how about I break and I talk about the project now? So, in the project with task 3, you are, you have the choice where you have basically 3 columns and your beam runs continuous over there. So this system here, 1's a pin, 2 a roller, you've got 4 unknowns. So what you need to do there is you need to draw the bending moment diagram for this system. When it comes to calculating the deflection, it's too complex to do. So you have been given the formulas. Let me find the project brief. So if you look in the brief here, at the very end of the brief, you have been given the formulas to calculate the maximum deflection, because it's a bit too complicated to try and work out how to do yourself. Now, in saying that, you've been given the formula here for the maximum in a simply supported beam with a UDL load, but in the brief it says you have to derive this equation yourself from first principles. Okay, and you've been given the third. I suppose since you've been given them, I can show you how to do it. Yeah, I can. You just want me to. Okay, let me go back. So how far did we get through this? Let's go from the beginning. Have you all started on project 3? No, shame on you. Okay. You have to design your truss now as a beam. You were given the task, as well as designing the main beam or the primary beam, you have also been given the task of designing the secondary beam. And the secondary beams are these beams that run in between the primary beams. And you've been told their spacing is 2 metres apart. So if I actually draw my bridge side on, there are my 2 primary beams. I've got my roofing in here. I've got my secondary beam here. And then I've got my concrete slab that sits on top. So there's my concrete slab. And under that, supporting it, is my secondary beam. Oh, bugger. Excuse me. Oh, I haven't got it on pen mode, that's why. Pen mode. Is my secondary beam. But if you look at your secondary beam and your primary beam, in both cases, well, for task option 1 and 2, you're just dealing with a simply supported beam with a uniformly distributed load on it. So basically, for your secondary beam, for the case where you have to look at the full span, for the case where you have the half span, you have the same beam. So when you generate your equations for your moment and when you generate your equations for your deflection, I want you to keep those equations in terms of L and W. So you don't have to keep on calculating. You don't have to draw me out 3 different bending moment diagrams. You calculate the bending moment once in terms of W and L here, as a function of W and L. You have that in as an appendix or in the beginning, And then when you change from your secondary beam to your primary beam, you can say, referring page 1 again, moment is equal to whatever WL, and you substitute in the new value of W and the new value of L. So people that aren't here are going to do pages and pages and pages because they're going to put all the numbers in. And especially you have to iterate your beam size. So for this secondary beam here, let me get a page. As this secondary beam here, oh, let me get a blank page. Excuse me. New slide. So, initially, I knew that would happen. Initially, you have a beam with a force W, load W on it, and part of that load includes the self-weight, which for a secondary beam you've been told is 20 kilograms per metre. Now you are going to work out the value of the bending moment diagram, yeah, as a function of W and L, and you are going to work out the deflected shape here as a function of W and L. So you are going to originally work out all the loading, the concrete, the steel, whatever it is, plus your 20. You're going to work out the bending moment. Once you have that moment, you're going to say M on Z has to be less than yield stress. You're going to find what Z you require, and you're going to choose a beam. Now, let's just say this isn't necessarily the secondary beam. We choose a beam, and the beam we need 20 kilograms per metre. That's not enough. Our beam now has to weigh 25 kilograms per metre. You're then going to go back in to this bending moment diagram with your new value of W, and you're just going to plug into your equation and calculate your new moment. So you don't have to redraw everything all the time. You say, here's the new load, here's the new moment, here's the new Z value. And if it's the same beam size, you stop, you've finished iterating. If you then find, oh, that beam's not big enough because I've increased the load, it now has to weigh 30 kilograms per metre, then you have to go in and increase your load again and iterate. Now that sounds very torturous. It's a 1 or 2 iteration process because the beam self-weight is a minor component of the load. So you do that for the moment and then for the deflection as well. You choose a beam size, you go and see what you need. If it's bigger or smaller, you put the new weight in, you stick it into the formula again. So it's quite an easy process really. So in this design, I've been through it, you're doing a strength and a deflection check, so an ultimate limit state check and a serviceability limit state check. Your deads and your live loads are the same for both, it's your load factors that vary. So when you have your bigger load factors in there, that's when you're going to do your strength check with your smaller load factors. You're then going to calculate a deflection and ensure for a simply supported beam, it's less than span on 250. Span is what? Span is the length between supports. So even when I have my third case, my indeterminate beam here, what is my span equal to? It's equal to L. It's the distance between supports. Okay? Okay. Now, you're used to this formula, My on I. In actual fact, this formula you'll see written as M on Z here. What is Z? Well, Z is simply I on Y. Now, I want you to use it in this form here, M on Z, because in the section tables here, you'll see a Z term right next to the I term. Now, if you were utilising this I term, you'd say Y. Oh, Y is a distance of half the section depth, so I have to know what section I have in order to put the right value of Y in. To save that headache, do it as M on Z, find a Z value, come into the table, find a Z value bigger than you need, come across and choose your size. So I think your bending, your strength check, you can all handle. Then we do a deflection check. We know why we're checking deflection. We get our equation for deflection, as I said, as a function of your loading and EI, and we ensure that's less than span. And in the equation, we know W, we know L, we don't have any P's in there. I is your unknown. So you solve for I, And then you would go in your table here and find an I value and then choose your section. So you are going to have two different choices of section, one that meets strength, one that meets deflection criteria. And which are you going to choose, the bigger or the smaller of the two? The bigger of the two, yep. And in the brief it says which is the critical load case. The critical load case is the one that dictates how big it has to be. So it's the one that's the bigger one. Okay, so you do this, I said simply supported beam, you're given the deflection information. This is too hard for you to work out yourself. So you're given the maximum deflection. This term here you have to derive from first principles yourself, not hard. Okay, so let's now look at, so when we look at our continuous beam here, option 3, you now know the continuous beam is indeterminate, and thus compatibility has to be considered as well as equilibrium to solve for the reactions, the ultimate limit state case. So using the theory we've learned, you'll solve for your reactions. Once you have your reactions, you can draw your shear force diagram and your bending moment diagram. Okay? So we'll leave that there and we'll go back to the theory. Okay. So I still haven't decided whether I want to do that example. I think I'll skip into the second one. I suppose in previous years I've always done it. Okay. Here's our question. Here's our beam. We have 20 kilonewtons per metre on it. I'm doing it with numbers. You're not going to do it in terms of numbers. You're going to do it in terms of W's and L's and then put numbers in. Okay? So, looking at our useful information, which support are we going to remove? Sorry, A, B or C? B. Okay, so let's say our primary beam now and this is the last question on the exam, by the way. It has two parts. One part relates to indeterminate beams. So this question always has an A and a B. And one part relates to indeterminate axially loaded members. This is our UDR load on here. And we want to know what that deflection is in the middle because B is in the middle here. So we've been given the formula for the deflection in the middle of a simply supported beam with a UDR load on. So we know this deflection here is equal to so. And we can't go just taking supports away, so we then are going to put it back as if it's a load. And then we need to know what this deflection here is. So this is our redundant system where we're putting away back what we took away. So we have a force By, and I've drawn it in small here, but going back here, the second formula you were given was the deflection in the middle of a simply supported beam. So we then say, well, that's cool. So we know the deflection here. P we write as By. In our formula here, it's P L cubed. This beam in here is L. So P L cubed, BL cubed on 48 EI. Sugar, I am doing it for you. And now we have to consider compatibility. So what we're basically saying is our primary system plus our redundant system is equal to our initial system based on the compatibility relationship that I'll call that delta primary and delta redundant, based on the compatibility relationship that the primary and the redundant deflection added together equals 0. So when I do substitute into those two equations, so now so this value here, when you substitute all your variables in here, is equal to 1,000 on 384 EI.
with a minus in front, and this here is equal to, when you substitute everything in, by on 48 EI. So over here, I then write minus 1,000 on 384 EI plus by on 48 EI. And note here, I've got a positive value in my redundant system because I've got upwards, and I've got a negative value in my primary system because it's down. And then solving for this here, that gives you a B value of 125 kilonewton. Now, once you know that value of By here is equal to 125 kilonewton, you can very quickly use equilibrium. All the forces in the y direction equal 0. So if I call that AY, BY, CY, I'll just get AY plus BY plus CY minus my load. 20 times 10 equals 0. And then when I take moments, you can take moments wherever you want at A. And taking moments at A, I'll leave you to do this. You solve for CY, and then you can solve for AY. So you can get those numbers yourself by plugging into your calculator. So now we can deal with redundant systems. I'm moving away from that one because I've spent too much time on that one. Here's our second one. Okay. We have a prop cantilever. Here's our useful information. Get your pens and pencils out and have a go at drawing the primary and the redundant and seeing how you can use that useful information. Yes? Yes. So, no, in that, also someone said, was L equal to 5 metres? What's L equal to? What you need to do is you need to go back and look at your useful information. So in this case here, L was the full beam. The full beam here, L was 10 metres. Yep. And in this formula here, L, that's L on 2, that's L. So L is actually equal to 10 metres. Yeah? Okay, this one. Go. Draw, have a go at drawing the primary and the redundant. Determine the reactions for the beam. You're just going to determine them in terms of EI and P's and L's. As soon as we give you an example that has no numbers in it, you fall apart, you crumble. Don't. I didn't want to do the work for you. I probably used different units as well. I probably changed the units I was working in. Yeah, well, you know what? It can be confusing because I've done too much for you. You can work through. Someone's just said to me, oh, Lizzie, what happened to this L here? You decide what units you're working in. I said L, yeah. So I'm going to leave you, because I feel I've done too much, to check the units yourself and try and get that answer. I have jumbled all my units up there, so you work that bit out. So maybe I can say I meant to do that on purpose to leave you something to do yourself. Okay. Go. There's your useful information. And I put a note here to help you along the way. Note, have a look at our problem. In our actual problem, we call the length AB and B, we can call this C. These two lengths are L. However, when we look at our useful information, when we look at these two formulas here, L is actually the full length. So if you want to know the deflection of the tip here, you would substitute for L, you would say, well, L is equal to 2L in my system. got all my useful information down there as well. So what do we want to take away? I'm not giving you any time. I'll just draw this while you're drawing it yourself. Okay, is that enough time to ponder? Not really, but we'll move on. Yeah, I've given you some time, so you've had some thoughts. Okay, our primary beam, we're going to take away our support. So this is the case where we have our load on there. So hopefully you all know it would deflect down like so. Now, where do we want the deflection? I'll call that C. At B. So it's very important you draw these, because in the tube, people go, oh, I calculated deflection there. I go, if you just drew it, you could work out where you want it. We want the deflection here. So looking at my formula, which one will we use, A or B? It's got to be B, okay? Because we don't want the deflection under the point load. We want the deflection at this point here along the beam. So here, we would say, well, X in our formula here is equal to L, and L in our formula is actually equal to 2L. So these are the variables in formula. Oops, variables. So thus, plugging into our formula here, I'll write this as VB. Oh. Erase. I'll stick to V's. So this is VB. So working out this value VB here, my load is P. I said X is equal to L, so X squared, L squared. And this L value here actually refers to the full length in the formula. But our full length is actually equal to 2L. Thus in here we would write 3 times 2L minus L. So plugging all that in there, you end up with 5 on 6 PL cubed on EI. Now my redundant system, I'm going to apply my force By as if it's a load. So how does this thing move? Well, it's going up. So this thing here curves up and actually beyond the point load, that bit in there is straight. But it doesn't really matter what it's doing in there, because this is what we're after. We're actually after the deflection under the point load.
So which formula am I going to use this time, A or B? A, okay? This is saying V max in this system, but what this actually is the deflection under the point load. So my beam here could continue out, and it wouldn't be V max anymore, but can you see the deflection's the same? Okay, so in this one here, VB dashed, we just plug into our formula here, turn it into a plus because it's up. BY, what is our length equal to this time? L. So L cubed on 3EI. And so now, compatibility is such that we're saying those two deflections, well, they have to add up to 0 because at B there's a support. So they equal 0 because at B there is no deflection. So very simply we'll say minus BB plus VB dashed equals 0, and from that we get a value of BY. So if you look at this and then calculate your other reactions, we have a force P here. This force here is 5P on 2. It's bigger than P. Why? Because of that seesaw effect. So if you do go on, and please do go on and calculate your other reactions, you would have a force down here of 3P on 2. And you would have a moment here equal to PL on 2. So you guys work those out yourself at home. Okay, let's move on to something a little bit more complicated. Every example I give you gets a bit more complicated. I've got a spring on the end now. Damn, so the deflection there isn't 0, is it? Damn, damn, damn. So in this one here, you would say, okay, there's my primary system, and we'll call this BY. There's my redundant system, but I'm not quite sure about my compatibility yet. But I'm not going to panic, as you might do in the exam. You're going to tell yourself, I'm going to breathe deeply, I'm going to calm down, and I'm going to get as much on the page as I can, because out of consequential marks I could potentially get 70% of the question marks. So whatever you do, don't panic. So I'm going to use a delta P again. So that's going to give you a delta P for primary. That's going to give you a delta R for redundant. Oops, what have I got there? Oh, there's my useful information. I'll stick to this page. Okay, oh, let's go back here. I've got delta P plus delta R. I'll write the equations here. Now, compatibility. They don't equal 0. What the hell do they equal? We can work that out. We have a spring here. What's our spring equation? F is equal to Kx. Yeah, looks familiar. What is F? F is By. K here. Well, that's my spring constant, which you would be given. And X here is the deflection here. So my deflection here will be a function of my reaction load divided by K, won't it? So when I now look at my compatibility equation, what are my two deflections equal to? Well, they're equal to By on K. Now, is it that simple? Kind of, but you have to be aware of your signs. This is the bit that stumps people. Okay, delta P, up or down? Down, so it's negative. Delta R, up or down? Positive. This spring value, which way is it moving? It's moving down. The load's on it, it's pushing it down. So this value here should have a negative sign in it. So this value here should be negative. People get their negatives and positives muddled up. So if you realise that's negative, so looking at our equations, so for our primary system, oops, this one has an angle. Our maximum deflection at the tip of our cantilever, that value here is WL to the fourth on 8 EI, where our beam is L long and our load is W. We've already come across the point load one. That deflection here is simply By. Once again, that's L cubed on 3 EI. So from compatibility, we said delta P plus delta R is equal to By on K. So I'm going to write here minus, and I better put a minus sign in front of that. That's a downwards. This is an upwards. And this movement here is a downwards movement. So, get it down, that equation. So you get your common factors together and you juggle it around and you move this to the left side and you move that to the right side and you divide by this and you divide by that. And your final equation looks like this. So this By, leaving it all general. That in the end is the value for this By force. Okay, so that's basically from this equation here. Now let's just look at this. We've reached the answer, so we're all right, we're all happy, but let's have a look. Okay, let's assume K is very flexible. We've just got a bit of foam under there. So in the extreme where my constant effectively is 0, By is effectively equal to 0 divided by 0, which is 0. Well, there's another term in here, 24 on EI, so is 0, which makes sense. This spring here is not stiff at all, so where's all the load being carried? It's being carried by support A. Let's go to the other extreme, where our spring stiffness is really stiff. And really stiff means it is now the equivalent of a simple support. And, well, I'm not going to substitute all the values in, but if that is the equivalent of a simple support, and I'm not going to do it now because I think I'm going to mess it up because I haven't got it on my piece of paper. If that's really stiff, you've got a big number here and a big number here, Oh, in the end, you're going to get a value for By. Believe me, okay? I'd have to work on that one at home, I'm afraid. Oh, hang on. No, I have it here. I have it here. Excellent. Okay, I take that back. Now I'm going to look really smart, and you're going to think I'm really smart. I didn't just admit I didn't know what I wanted to do. Our spring stiffness is really big. So therefore, this term here is much bigger than our 24 EI. Okay? So therefore, for By now, we would just have this big term here and that big term there, which simplifies down, bye-bye, to that term there. And that's based on the fact that 24 EI is very small. And that is the reaction you would get if you had a pin support there. Okay? So having that, well, a support there that can't move. So this support here can pick anything. The range that it can pick up is 0 up to a maximum of 3 WL on 8. So what's our total load down here? WL. So with one end being a fixed support, can you see this fixed support would pick up far more load? This fixed support here would pick up as much as WL to as little as 5 WL on 8. But either way, it always picks up more than half because it's stiffer, it's a fixed support. Make sense? Do we need a short break before we do another problem? Okay. I'll give you 240. You can come and ask me questions if you wish. Dish.
For one is we take the point load for the equations, and for the second equation we generally don't take the point load. So
Yeah, because you see what we're saying is this plus this equals that.
yeah,
So if you put the load in again,
it will make sense.
then it's twice the load. Yeah. So in your primary you have the loading, in your redundant you have what you've taken away. Yeah.
Thank you. Okay.
If we're getting a Z value for the secondary beams, that's much smaller than what's on the table.
Yeah.
Do we use this loss?
Yeah, that's all you can do. You go in your shop, you say, I need something really small. If you look at the lowest size in the table, it's only like 200 to 300. So basically, that's the size here. If this was a real job, you'd go, I'm going to try and find a small beam that's not a UV. And see if I can have a square hollow section or something that's that way. So yeah? But you're limited to UV.
When we find W, we got the ULS. That's what we're going to do, right?
Sorry?
But when we use it, because obviously we're trying to find the Z
Are you
value.
finished? Is that...
No, we are in the same.
Okay.
Yeah. We're in the same group. Yeah, so we're trying to find the Z value, obviously.
Yeah.
And that's the moment over, of the stress value.
So once you get stressed, you realize you take it to 350.
Yeah, we've got 350, but like when we use WL squared on 8, we use W as the ULS.
Yeah.
Right. Okay, and then we took like not just the self weight of the beam, we took the concrete, everything on top of it.
Yeah.
And yeah, we still got like
So you don't need to iterate to look at the secondary beam. Because there's nothing else to iterate to. So that's it.
because so we got it in kilonewtons per meter, and then we converted it to newtons per millimeter to because of the yield stress, because yield stress goes in 350 MA, and
But your moment is kilonewton meter.
yeah, and we
Kilonewton per meter.
yeah, we converted to kilonewtons per millimeter, newtons per millimeter.
No. What I'm saying is 1 kilonewton per meter is equal to 1 newton per millimeter.
Is it?
Well,
Or is it times
okay,
10 to the power
instead of a kilonewton, I write a newton. So instead of a kilonewton, I've got 1,000 newtons, haven't I?
6? Yeah.
Instead of a metre, I've got 1,000 millimetres. The 10 to the 6 comes in when it's the moment. So a moment has units of kilonewton
Oh,
meters.
right.
So when it comes
Not
to the...
per meter, it is...
No,
in-
1 kilonewton metre is 10 to the 6 newton millimetre. But 1 kilonewton per metre is 1 newton millimetre.
Right,
Yeah?
okay. And then then the Z value, it was in times 10 to the power 3.
Yeah,
You got to make sure you do that, right? Okay, cool. I think we have to redo our calculation then. Alright, cheers.
Yep. Also, when we use the WL squared L, do we
So
take
you
that as...
derived that formula?
Not yet. We have to go back and do that. Yeah. Do we take the L as the full length?
So that's what you derived it as. Yeah? All right? Okay, we'll start up in, yeah. Is it fine?
With the second done the iteration for the
Yeah, so that's fine. That's what I'm saying. You can use that equation given to you by you just need to derive it once. Yeah. Yeah, and then you can say, oh, this is
You know how this sits in between the I-beams? Yeah, then what's load on the I-beams if it just sits on the cross beams?
well, what's what? So if you're doing a load part, your way here goes into the concrete, and the concrete goes into the secondary beam, and from the secondary beam, yeah? Pretty fine? It's too late.
For the bridge, I basically did it myself. They wanted to meet up last minute, so I was just going to be, I did it all. Yes, yeah.
Okay, let's get going. Okay. Okay, here's an even harder one. Oh, it looks harder. So here's my tip for the exam. I have what I call scare questions. A question where you look at it and you go, but every question on the exam you can do. Okay? So sometimes they're made to look ugly just to scare you, but you tackle them the same way, they're no more difficult. So this I would call a scare question. The first time I saw this, I went, God, what do I do? Have a look at it for a minute. I should have put it up before the break so you could have had a look at it. Okay. Here, I'll put it up with the useful information. Oh, no, read the question first. Determine the reactions. Okay, we have three supports, D, A and C. Okay, and again, here's your useful information. Come on, draw some redundants and primaries and go, okay. Test yourself, push your mind. Go, I'm really going to try now before Lizzie does it to see if I get it right. So if I'm thinking through it right, I'm going to feel really good about myself. Thought about it? Don't want to think anymore? Okay, I'm kind of splitting it in two. I'm kind of going to look at it, I'm just extending that distance in there where the ball is. So I have a load here, P, and I have some support here. I'm going to call it B. So of that load P, some of it will be transferred into the simply supported beam. So if that force there is B, then this reaction here will be P minus B. Yeah? Now if there's a force up here B, there's a force down here B. And because this is symmetrical, that will be B on 2, and that will be B on 2. Yes, Lizzie, but we don't know what B is. You're right. Okay, so let's say, okay, I have to take a support away, so I've got a cantilever up here. I'm going to call that my primary system. And I know when I take things away, I have to put them back. So I know I'm going to get some partial marks here. I'm going to call that B. That's the reaction I've removed, and that's P. Okay, so it deflects down like that. And from my useful information, delta primary, up here, that's equal to minus P. Now can you see up here, even though I haven't circled it well, in our useful form information, that length is L. In my beam, that length is L on 2. So that's when I plug in here, I'm going to put in L on 2, all cubed, on 3EI. Now effectively I've got the same thing here, but I have a B term in here. So my redundant, well, it's a plus this time, plus B, same thing. So where is this getting me? You don't panic, I've got a primary, I've got a redundant, now I need to think about compatibility. Okay, compatibility. My primary plus my redundant, do they equal 0? No. So point B is moving down, isn't it? How much is it moving down? Isn't it moving down that much? Assuming this P force is equal to B? Yeah? So I'm going to equate that to that deflection with a force B on it, which, looking at my useful information here, the length of my beam is now L, and my useful information, it's L. So I'm going to call that, is it upwards or downwards? It's downwards. So minus B L cubed on 48 EI. I'm going to write that out a bit neater on the next page. So I'll write it as, hang on, let me give you another page. Where am I? Okay. So I hate that. So I'm going to say primary plus redundant equals the deflection of the simply supported beam. So we said our primary was downwards. We said our redundant was upwards, so it's a positive value. And we agreed that our net deflection was downwards. So just expanding everything out. It looks really messy. But when you actually cancel out your L's and your E's and your I's, you get minus 2P plus 2B is equal to minus B. So B therefore equals 2P on 3. So therefore the force coming down into this part of the beam is 2p on 3, and the force up that stays up here is effectively p on 3. And so if that force is p on 3, that reaction here must be p on 3. If the force coming down here was 2, you have a reaction here p on 3 and p on 3. So in effect, the simply supported beam is carrying 2/3 of the load, and the cantilever is carrying 1/3. And that's based on the lengths being the same and the EIs being the same. If this then had a stiffer EI, you could see down here, it would then attract more load. So it can attract more load by the fact that this EI is different. Okay, there's no point starting on the final problem. However, I would say maybe you could read this problem. It'd be great. For the next lecture, you had a read of the problem, you attempted it. Why not? Why not do something different? Have a good rest of the week.